For years, there's been one unbreakable rule in artificial intelligence. If your AI is too slow, you buy more hardware. More chips, more power, more money, bigger data centers stretching further into the desert. That rule has built trillion-dollar companies and reshaped the global economy around a single piece of silicon coming out of Taiwan. But what if the rule itself was never actually true? What if the entire foundation of the AI race, the assumption that speed means more electrons racing through more transistors, was just proven wrong, not by a bigger chip, but by an entirely different kind of light? Chinese researchers just built processors that don't use electricity to think. They use photons. Beams of actual light doing calculations at a speed and efficiency that traditional chips, including NVIDIA's best, cannot physically match. And in specific, real published tests, these new chips have already beaten the industry's leading hardware by anywhere from several times over to more than 100 times over, depending on the task. Stick with me, because if this technology scales the way its creators believe it can, the GPU, the chip that built the entire AI industry as we know it, may not be the end of this story after all. Let's start with the fundamental problem that's been quietly suffocating the AI industry for the last few years. Because you can't understand why this breakthrough matters until you understand exactly what wall these researchers were trying to smash through. Every AI model you've ever used, every chatbot, every image generator, every recommendation algorithm runs on hardware built around traditional electronic chips, the kind NVIDIA has spent decades perfecting. Those chips work by moving electrons through transistors, tiny electrical switches flipping on and off billions of times per second. It's an incredible engineering achievement, but it comes with two brutal physical limitations that no amount of clever engineering can fully escape. First, electrons generate heat, a staggering amount of heat. That's why modern AI data centers need industrial cooling systems running around the clock, and why training a single frontier AI model can consume as much electricity as an entire small city. Second, electrons are, relatively speaking, slow, at least compared to the fastest thing in the entire universe, light. That second limitation is exactly what a growing wave of Chinese research institutions has decided to attack head-on by building chips that abandon electrons altogether for certain tasks and instead compute using photons, the actual particles of light. The idea itself isn't brand new in theoretical physics circles, but actually building a working physical chip that computes with light and does it well enough to challenge real GPU performance is an entirely different engineering achievement. And this year, multiple Chinese research teams have published results claiming exactly that. Let's walk through what's actually been demonstrated, because there are several distinct projects here, and separating them clearly matters if you want the real picture instead of a blurred, exaggerated one. One of the most talked about is a chip called Accel, developed by researchers at Tsinghua University, one of China's top engineering institutions. Accel is a hybrid design, combining photonic components, meaning it computes using light with traditional analog electronic parts working alongside it. In published testing on image classification tasks, Accel demonstrated performance of around 6 petaflops, an enormous amount of raw computing throughput, while consuming a tiny fraction of the electricity a comparable traditional GPU would need for the same job. In direct comparisons, against NVIDIA's A100 GPU, a chip that until recently sat near the top of the industry for AI computing, Accel delivered performance gains reported at multiple times faster, specifically on computer vision workloads, the kind of tasks involved in image recognition and classification. Then there's an even more ambitious project called LightGen, developed jointly by researchers at Shanghai Jiao Tong University and Tsinghua University, with the full results published in the prestigious scientific journal Science. Unlike Accel's hybrid approach, LightGen is described as a fully photonic chip, built around more than 2 million individual photonic neurons, computing units that process information using light rather than electricity, from start to finish. According to the published research, LightGen demonstrated performance on specific generative AI tasks, image synthesis, and image generation workloads more than 100 times faster than conventional GPU hardware handling the exact same job. 100 times. Let that sink in for a second, because that's not an incremental improvement. That's the kind of leap that, if it holds up and can actually be scaled into real-world deployment, doesn't just nudge the industry forward. It rewrites what's physically possible for specific categories of AI computation. And this isn't the only front where Chinese researchers have been pushing photonic computing forward this year. In July, a separate team at Peking University published research demonstrating an entirely different application of the same underlying light-based principle, not building an individual photonic processor from scratch, but instead using photonics to solve the communication problem between multiple existing chips. Their system links standard electronic processors together using an all-optical interconnect, essentially letting separate chips talk to each other at the speed of light instead of through traditional, comparatively sluggish electrical wiring. The core innovation here involves specially designed silicon photonic transceiver components capable of converting electrical signals into light and back again at extremely high speeds, allowing an entire cluster of chips to function more like one enormous unified processor. According to the published results, this approach delivered speed improvements up to 100 times faster for certain AI workloads, using a fraction of the total computing power that would normally be required. And there's an even more ambitious detail buried in that same research. The team described a future vision involving something called a macro chip, where instead of manufacturing one enormous, extremely expensive processor using cutting-edge lithography, you could instead mass-produce hundreds of smaller, cheaper chips and stitch them together onto a single wafer, all communicating with each other through these same light-speed optical connections. If that approach actually scales the way researchers envision, it could meaningfully lower the manufacturing barrier to building extremely powerful AI computing clusters, since you'd no longer need the absolute bleeding edge of chip fabrication technology to assemble something functionally comparable. There's also a separate, even more exotic project worth mentioning, developed by a Chinese firm called ChipX, the chip hub for integrated photonics Explore. Their system takes this concept even further into the realm of optical quantum computing, using light particles specifically as carriers of quantum information rather than traditional binary data. According to reporting from the South China Morning Post, the chip's developers have claimed performance up to 1,000 times faster than NVIDIA GPUs on certain AI workloads, and the company claims its design is already being used in specific industries, including aerospace and finance. It's worth being clear, though, that quantum computing claims in general deserve a healthy dose of scrutiny and patience, since the entire field remains in a genuinely early, rapidly evolving stage, and dramatic performance claims in quantum computing research have a long history of needing significant real-world validation before they translate into practical, widely deployed technology. Now here comes the crucial reality check, the part of this story that separates a legitimately exciting scientific breakthrough from a wildly overhyped headline. And it's a distinction every single one of these research teams has been careful and honest about themselves. None of these photonic chips are general-purpose replacements for a traditional GPU. Not XL, not LightGen, not the Peking University Interconnect System. A traditional GPU, the kind made by NVIDIA, functions essentially like a flexible, programmable calculator capable of handling an enormous range of different computing tasks, from training massive language models to rendering video games to running complex scientific simulations. These new photonic chips are fundamentally different in character. They're closer to purpose-built specialists, extraordinarily fast and efficient at one specific category of task, image and video generation, computer vision, certain narrowly defined matrix calculations at the mathematical core of neural networks, but without anywhere near the flexibility to handle the full, sprawling range of computing jobs a modern GPU is expected to perform. Think of the difference this way. A conventional GPU is like a highly skilled general contractor capable of framing a house, wiring the electrical system, laying plumbing, and finishing drywall, all with the same core toolkit adapted to each different job. These photonic chips, by comparison, are more like an extraordinarily fast, precision-built machine designed to do exactly one specific task, say, stamping out a particular metal part, at a speed and efficiency level no general-purpose tool could ever match, but genuinely incapable of doing anything outside that one specialized function. That distinction matters enormously for how this technology is actually likely to get used in the real world. Nobody serious in this field is currently predicting that NVIDIA's GPUs are about to disappear from AI data centers. What's being predicted instead, by the researchers themselves and by outside industry analysts covering this space, is something more nuanced, a future where photonic chips increasingly get deployed alongside traditional GPUs, functioning as specialized accelerators handling specific, narrowly defined workloads, particularly generative image and video tasks and other inference-heavy jobs, while general-purpose GPUs continue handling the broader, more flexible range of computing work everything else requires. There's also a genuinely fascinating manufacturing angle to this story that deserves attention, because it connects directly to the broader geopolitical chip war that's been reshaping the entire tech industry. One of the most striking claims about Echicell specifically is that it can reportedly be manufactured using older, less advanced chip fabrication processes, the kind of manufacturing technology Chinese semiconductor companies, including SMIC, already have reliable access to, without needing the absolute cutting-edge lithography equipment that American export controls have been specifically designed to keep out of China's hands. If that claim holds up at meaningful commercial scale, it represents a potentially significant strategic advantage, a path toward genuinely competitive AI hardware performance that deliberately sidesteps the most advanced manufacturing bottleneck, currently constraining China's broader semiconductor ambitions. Instead of racing to match Western chip fabrication technology node for node, this approach essentially asks a different question entirely. What if you didn't need the most advanced manufacturing process at all, because you're computing with an entirely different physical medium from the start? So, stepping back, what does all of this actually mean, and how excited should you genuinely be? The honest answer sits somewhere between the breathless YouTube headline promising the end of the GPU era and the more skeptical dismissal that treats this as just another overhyped lab demonstration destined to go nowhere. These are real, published, peer-reviewed results, with LightGen's findings specifically appearing in the journal Science, one of the most rigorously vetted scientific publications in the world, which lends the underlying research genuine credibility rather than leaving it as an unverified press release. The performance gains being reported, ranging from roughly 4 times faster on some tasks up to over 100 times faster on others, are not fabricated marketing numbers. They represent real laboratory results on specific, clearly defined workloads. But the technology remains in a research and early prototype stage, not a mature, widely available commercial product, sitting on data center shelves, ready to replace your existing infrastructure tomorrow. Scaling any laboratory breakthrough into reliable, mass-manufactured hardware that major cloud providers and AI labs are willing to build entire systems around typically takes years, not months. And plenty of genuinely impressive lab results throughout the history of computing have quietly stalled out before ever reaching that kind of real-world industrial scale. What makes this moment genuinely significant, though, isn't necessarily that the GPU is about to vanish overnight. It's that a fundamentally different approach to AI computing, one that sidesteps the heat and speed limitations baked into traditional electronic chips altogether, has now been demonstrated as real, working, and published science, not just theoretical speculation confined to physics journals. And it's emerging specifically from Chinese research institutions, at a moment when access to the world's most advanced traditional chip manufacturing technology has become an increasingly contested, increasingly restricted resource. That combination, a genuine technical breakthrough colliding directly with an active, ongoing global chip war, is exactly why this story deserves real attention rather than either blind hype or dismissive shrugging. The AI industry has spent years assuming the path forward always meant more electrons, more heat, more power plants, and more advanced silicon fabrication. Chinese researchers just demonstrated, with real published data, that there might be an entirely different path available, one written in beams of light instead. Whether that path scales into something that actually reshapes the global AI hardware industry, or remains a fascinating but narrow specialist tool sitting alongside traditional GPUs for years to come, is the genuinely open question the entire industry is now watching closely. If this kind of story matters to you, the kind that separates the real breakthrough from the hype and actually explains what's happening underneath the headline, hit subscribe so you don't miss what comes next, because this race is only just getting started.